vacuum. It's in vacuum. Vacuum is the absolute thing. Vacuum is like 0, right? So if your ambient vacuum is under expansion, oh, of course, they also brought up a good point that reminds me. Now, what happens if it's under expansion? This is between 5. Again, this is between C to 5, right? That's why. Now, what happens if it's below 5? Below 5, this is what you see. Because it's under expanded. So that means the flow continues to expand outside the nozzle. Right? So no shock wave anywhere. You can say flow continuous expansion outside nozzle. That's good. Yeah, thank you. Thank you for bringing up the point and that reminds me of. Like this is shock wave outside the nozzle. Here's the expansion outside the nozzle. Then what would happen here is that if this is the symmetric plane, then what you have is expansion, and then expansion, and then the reflective wave is again expansion, and then expansion, and then you expand, and then you expand. You expand too much. Shock, 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 and you got shock too much. Your pressure is higher than the ambient. Expansion, 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 and then you expand too much. Shock. So the sequence is kind of similar, but it just one starts with obviously shock, one starts with expansion, and then it repeats itself. Now, most likely for the flight vehicle that you want to design is you would want to have conditions below 5. Right? Most likely that's what you would have. And especially for a rocket or for a vehicle that you are going to launch into outer space, that is definitely the case, right? Because as you rise up, the pressure, ambient pressure gets lower and lower, right? So even if you design it as perfect expansion right at a sea level, it eventually becomes under expansion. But because the pressure, the ambient pressure decreases with altitude. Make sense? And you normally don't design it for perfect expansion. I would not, because I would not know other practical considerations in there. But because you design it for perfect expansion, what happens if it's at a short time you have shock wave right in the nozzle, right? Or very near to the nozzle exit, that is certainly would affect your exhaust velocity. Right? And you don't want it, because if you have a decreased exhaust velocity, you don't have the thrust that you want. Okay. So to be on safe side, you probably want to design this is somewhat underextended. Make sense? Okay, questions?
Professor?
Yes.
For point C, since the normal shock is parallel to the exit plane, does that mean at that point C, the exit velocity is Mach 1?
value is less than 1. Shock wave always occurs in such a way that a supersonic flow becomes a subsonic flow. In the limiting case, you will have upstream Mach number 1.0001 and downstream Mach number will be 0.9999. Or Mach 1 and then Mach 1, but then there's no shock wave. Right? By definition, shock wave will cause some pressure increase, and the Mach number will go down from supersonic to subsonic. So you will never have exit Mach number equal to 1 in a conversion diversion nozzle. But in a conversion nozzle, that can happen, right? Because that's where it should happen. Your exit is the narrowest part of it. If Mach number is going to happen anywhere, it's right at the exit. If it's going to happen, right? That means if your pressure ratio is high enough or ambient pressure is low enough, then you would have the choke nozzle and Mach will be equal to 1 at the exit. That's the narrowest part. That's where dA is equal to 0. But in a conversion diversion nozzle, dA equal to 0 at the throw. So this, if Mach number equal to 1 is going to happen anywhere, that is where it is. It cannot be at the exit. You will either exit with a subsonic flow, or you will have an exit with a supersonic flow. So by definition, if you have an oblique shock wave like here, and your exit plane is here, right? So flow here is still supersonic. Not just that, even after oblique shock wave, it could still be supersonic. So you for conversion diversion nozzle flow, you either have a subsonic exit or you have a supersonic exit. You will not have a sonic exit. That's a good point too. The difference between conversion and diversion nozzle. That's also one thing you can tell while observing. Yes.
I just want to make sure you understand, like right from the chart. Is it not possible to figure Mach 1 in the probe? Is it Mach 1 your max speed of your probe?
You cannot do anything else. Now, we will deal with this later on. If you have a supersonic inlet, it is possible that your flow will have supersonic flow. We deal with it. Remember, Mach number is a ratio of area also, right? So now if I'm pushing the flow through a nozzle, like using a reservoir, that means I'm going from subsonic flow all the way down to possibly Mach equal to 1 in the flow. And remember, we have an example where I said that, well, if the nozzle exit is Mach equal to 1, because your back pressure is sufficiently low, then you will have your inlet to the nozzle, the Mach number would also increase. So in a conversion diversion nozzle, if I have sufficiently high pressure ratio, I can push Mach equal to 1, which is condition 4 and below, right? And 4 and above, you will not have Mach equal to 1. However, in this case, your Mach number can increase. Here, Mach equal to 0, that goes without saying, right? And here, Mach number, you will increase to, I don't know, any value, 0.3, 0.5. Here, maybe 0.7, 0.8, 0.9, 0.99, and 1. As you lower the pressure or as you increase the pressure ratio. This is because you accelerate the flow from 0 velocity toward the nozzle, then at the flow you can at most have Mach equal to 1. So Mach equal to 1, once this is Mach equal to 1, if I know the inlet area, I can calculate the Mach number here. Remember, right? Remember your Mach number is equal to function of gamma A over A star. Right? That's in the table. Right? So all these values are in the table. Right? So that means what? For a known gas, if I know the area ratio, I know the Mach number. Exactly here. I can calculate Mach number at any point along the way. As long as I know the cross-sectional area, and as long as I know the A star. Even though A star may not exist in the geometry of your problem. Right? Again, here is the same. A star is kind of like a sea level, even if you don't get to see the sea right there, you know what sea level is. Okay? But to answer your question, in a supersonic diffuser or supersonic inlet, you will have a flow coming in supersonic, not like here, the flow coming in subsonic. You have the flow coming in supersonic. Let's say, if I know the inlet area and I know the flow area, if the flow area is not small enough, then you may still have supersonic flow at the flow. Because your inlet area divided by your flow area should give you one Mach number, one only, right? Because then isentropic flow condition is that your Mach number for a known gas, in this case, let's say the supersonic diffuser or supersonic inlet for a fly vehicle in the air, you already know the gamma. Then the area ratio should give you a unique Mach number, right? And so you will have this inlet geometry and the flow geometry. You take the ratio. Now you say if the Mach number is going to be 1 in the flow, the Mach number at the inlet has to be determined by the area ratio. And if your flight Mach number is not that, then you will not have Mach equal to 1 in the flow because it doesn't match. So in diffuser, you have this problem that it would not match. So the diffuser design and the diffuser operation is a lot more complicated than nozzle, as we will discuss in about, hopefully, 2-3 weeks. Okay, so the diffuser operation is not as simple as a nozzle. So if you are doing a supersonic flying, some of you guys may be flying a supersonic aircraft in the future, then you will be taught there is this thing called overspeeding, although you will not get any tickets. It's overspeeding, meaning what? Your Mach number, because during your flight, you go from 0 to whatever supersonic you want to be, right? So you go from, of course, initially subsonic, forget about that part. No fun, right? Now, once you get to supersonic, you say, hey, if my flying Mach number is going to be 1.5, but the geometry during the 1.4, the geometry is designed for 1.5. You want me to fly at 1.4, and during the transient period, then there will be crazy things happening like shock waves and so on for the flow coming into the inlet. But you know, shock wave is bad because you lose the stagnation pressure. That means even with your engine compression and all that, your compression ratio is more or less fixed. So if you compress something that is already low or you compress it, it's not very useful, right? So you try to prevent the pressure loss. So you want to fly at such a speed that it will come in just exactly right after the geometry would have. So one operation to do it is to overspeed, meaning that I purposely ramp up my Mach number to a certain value, maybe 1.8, to exceed my design Mach number, so the nozzle will swallow the shock wave. And once the shock wave is swallowed into the nozzle, then you can slow down to 1.5. Okay, just to give you a little bit of idea, so this is a good thing, right? You hear it, even though you may not exactly understand it, but in 2 weeks you say, oh, yeah, no, I understand. Now, of course, it cannot be taken as such a simple matter, right? Because the reason that you want to fly supersonic speed is not that you just want to cruise at that speed. So that if you are in a compact mission, you don't have a steady state fly, right? By definition. You know, it's crazy things, right? So you would not definitely have that. So it's a lot more complicated. So supersonic flying is really very, very complicated, especially for military aircraft. Because you make 1.3 at one moment, 1.5 at one moment. Very crazy. So that's a very challenging. Any more questions? Now let's try to have an example. And also, before that, you need to know that to choke the nozzle, in a sense, all you need is below 4, right? The condition is below 4. Because the Mach equal to 1, even if you further reduce the ambient pressure or you increase the reservoir pressure, Mach is going to be 1 in there. But you remember, when Mach is equal to 1 at the throat, if you increase the reservoir pressure, that means your mass flow rate will increase. Right? If you decrease the ambient pressure, the mass flow rate will not change anymore. Because the mass flow rate, remember that choke m dot equal to T over square root of RTT. A star is equal to LTH, square root of gamma plus 1 over 2 to the power of gamma plus 1 over 2 1 minus 10. This is the same as in conversion nozzle. So let's say once the nozzle is short, if you decrease the ambient pressure, it doesn't change the mass flow rate. But if you raise the reservoir pressure, then it changes the mass flow rate in the sense that PT increases. Right? Okay. Let's have this example. The CD nozzle, this is shorthand for conversion diversion nozzle. It is used to deliver air, of course, down here 1.4, from a reservoir at 300K and 20 megapascal to 200 kilopascal. So let's say you use a conversion diversion nozzle to deliver some air. Maybe through a pipeline and somewhere there's a conversion diversion nozzle. Wanted m dot equal to 20 kilograms per second. Question 1, ATH, what would that be? Second, AE, meaning that the cross-sectional area at the exit. Third question, PE equal to what? PE equal to what? You can say PE equal to what? Asked. So you want this mass flow rate, let's say, without any shock wave. You don't want any shock wave. So, the first thing you do is a 1D flow and steady isentropic. That's what you want to do. So this is so simple because m dot we already did, right? M dot is equal to PT square root of RTT A TH, because this is equal to A star now, right? Square root of gamma times gamma plus 1 over 2 over gamma plus 1, 2, and plus gamma. So here you have 20 kilograms per second. I would encourage you to put in all the units in there, because if you cannot cancel out all the units to give you this, you know something is wrong, right? So we as engineers, units are important because that's the first check whether you are putting in all the right parameters or not. Okay. So this is equal to, your PT is 20 megapascal. 20 megapascal is 20 10 to the power 6. What? Newton, right? Newton meter squared. Divided by R, it's 288 or 87. Some folks use 287, some folks use 289. I use 288. Joule per kilogram per Kelvin, right? And joule is what? Newton times meter per kilogram per Kelvin, right? Times your TT, reservoir pressure, 300 Kelvin, times ATH that you don't know, square root of 1.4, and this is 1.4, so 1.2, this is 2.4, this is 2.4, this is minus 0.8. So it becomes what? 2.4, this is 3, minus 3. Okay, now so what I'm going to do, K goes away, right? Oh.
Yes, sir.
And you know Newton is equal to 1 kilogram per meter per second squared. So you plug that in. I trust you can do that. Take care of all the units. So you have an ATH is equal to 4.29 10 to the power minus 3 meter squared. This is equal to 42.9 centimeters squared. And if that is pi r squared, pi is equal to 3.14, so we divide that, it's about 14. So the radius is about slightly less than 3 centimeters at a throw. So we probably have a pipe like this. Okay, at a throw. Now, the second part, what is your AE? So this is the first part. Now, second part, isentropic, PP over PT is equal to PP over PT is equal to 200 kilopascal divided by 2 megapascal, 20 megapascal. So that value is pretty small. I'm sorry, I should This is really 2, not 20. 2 megapascal. 2 megapascal. So it's 2 megapascal. Oh, 20. Sorry, every zero should go. It's still 20 kilograms per second. So this is equal to what? This is equal to 0.1. So if you look at this value, that means your ME nozzle exit. Yes.
I'm just wondering, why can we equate exit pressure or back pressure?
Yeah, that's what I was gonna ask. Since you said no shockwave, so should it not be that the exit pressure is higher than the back pressure? Or
Oh yeah, this is, yeah, you asked for example, it's perfect expansion, this is it. You want to deliver the air at 200 kilopascal. Right? So you want to deliver your pressure okay. You want to deliver your air
no shock
to a
in the
location
nozzle.
where the pressure is 200
That's right.
Perfectly expanded, the shock's on the
kilopascal.
outside. There is no shock.
So deliver from a reservoir
Perfectly expanded.
Okay.
at 300 K
no, I understand, but
and
it's
2
perfectly
megapascal
expanded, no
to
shockwaves,
200
and that's the
kilopascal.
pressures are not the exit pressure. Sure.
I should have considered this kind of, this is where you want to design it for. But of course, in your real operation, you may not have it, right? Okay, so because of this, you use your table, you find out your ME is equal to 2.15. And if ME is equal to 2.15, your AE over A star is equal to 1.919. So then you will have your AE equal to 82.38 centimeters squared, which is larger as it should be, right? And in this case, PE over PT is equal to, well, that's already known, right? So your PE really is equal to PE equal to PG equal to 200 kilopascal. But your TE over TT is equal to 0.5196. So that means your PE is equal to 155.88 Kelvin. So VE is equal to ME square root of RTE is equal to 2.15 times square root of 1.4 times 288 times 155.88. This will give you 538 meters per second. And you imagine this is a rocky nozzle, that's what you will find also. Yes?
Where'd the 0.5196 come from?
Table.
Table?
Yeah. Isentropic flow. Or you can do this, right? And you can also use this. Okay, a few comments here. Now the reason you use 2AVA is because usually you know your gas constant is equal to 0. Universal gas constant is 8.314 kilojoule kilogram per Kelvin, right? And you divided it by air, the molecular weight is per kilomole, you have 28.8 kilograms. Even usually we said, oh, air has a molecular weight of 28.8, but that's gram, right? Per mole. But you're talking about kilomole, right? So you have your gas constant is equal to universal gas constant divided by molecular weight, right? So this universal gas constant is equal to 8.314 kilojoules kilomole per Kelvin. Now this M, let's say here, is 28.8 kilograms kilomole. So when you divide these two, you will have R equal to 0.288 kilojoules, kilograms per Kelvin. This is equal to 288 joule per kilogram per Kelvin. Now this may sound very trivial, but over the years, some students making mistakes here. Here, you know, in our SI units, if you go by meter, kilogram, and second, your energy will come out to be joule, your force will come out to be Newton. Okay? And your power will come out to be watt, for example, right? SI units, all nice. Okay? I like British or English unit. But you need to know, in SI unit, your fundamental unit is kilogram, it's not gram. So here, you cannot say, oh, here's a K. Here's also a K. You don't do that. Okay? That's why you have 288. It's not 0.288. Make sense? You cancel the units, not the matrix. Okay? Now, so if this is working, then you can start calculating the thrust now, right? So the thrust will be equal to m dot times E, because it's perfect expansion. That's your thrust, right? That's your thrust. So you can find out what's the force. This will be equal to 10,780 newtons if it's a rocket. Why don't you do this for yourself?
What's the symbol for ghost?
T. Oh, sorry. I don't know, grammar. You guys don't like cursive anymore. If you read newspaper like New York Times or, I went to school in Michigan, so first newspaper was Detroit Free Press, and Detroit Tigers has that D. What is on their chest, you know? And then, oh, that's D. Yeah.
How can the exit velocity be higher than the speed of sound if PE over PC is only 0.1 and not higher than 4?
What do you mean by speed of sound?
Isn't the speed of sound in air only 343 meters per second?
340. You know that?
I believe so.
That's the sea level condition. This is so. Speed of sound changes with temperature, remember?
Oh, okay.
Speed of sound is not like gravity, okay? There is no set value of speed of sound, okay? Now,
Gravity changes distance too.
so it could be supersonic and still very low speed, right? Let's say your temperature is close to 0. You say, oh, I'm flying at Mach number 2.5. But that's slower than my car. It's possible, right? Okay, so here your temperature, your speed of sound is really gamma RTE at that location. So, just so for your information, your speed of sound actually changes throughout the location. Because the local temperature changes. That's also a nice thing to know. Speed of sound is not a set value. So when we every day we say, oh, this is supersonic, we talk about a very generic value, like, okay, sea level, that's about 340 meters. Now, one thing here is, you look at this temperature, it's pretty low, right? 155 K. What does that mean? That's about 120 degrees, minus 120 degrees C, almost. It's pretty cold, right? Now, of course, this question can be reframed that your reservoir temperature can be higher. For example, you deliver this air to a supersonic wind tunnel, then it's 155 degrees C. You know what happened? The moisture would already freeze into little ice balls. Okay. In the 1990s, I did supersonic research here. I use our supersonic wind tunnel, but I want to do the noise coming out of the supersonic jet. So I need to produce a supersonic jet, and by the way, it was underexpanded. And we did not have the heated supersonic wind tunnel. So in some applications, when they do research, they need to heat up the wind tunnel so that by the time you reach the supersonic speed, the temperature is not too low, so that the moisture will not condense into little ice. I can tell you this is so interesting. When I was doing that, because it's not heated, so our reservoir was outside, and given that Florida is very hot, it can only be 300 something Kelvin, right? Not like 400 or 500 Kelvin. So when it comes down, it comes out to the jet, the temperature is roughly that low, and because it's underexpanded, so it continues to expand, so the temperature is even lower. So what happened was that the moisture condensed into tiny ice, you cannot even see it. So what happened is that my students and I just want to have a feeling of it. So we put our hand into this nozzle. The nozzle X is only 1 centimeter, and it's a converging nozzle. So it comes out Mach number equal to 1, continue to expand to about Mach number equal to 1.8. But put your hand there, ooh, this 1 centimeter nozzle actually gives you a lot of thrust already. You barely can hold your hand there, right? I say, hey, that's pretty cold. And I say, oh, because you use your hand here, it's not very sensitive. So let's keep my face in there. So the jet comes out, and you feel like there are these tiny bullets shooting into your face. Because this little tiny bit ice is a stinging. You feel like you are being poked by needles. Unfortunately, it's so small. The water is condensed into ice. Because using my hand here, you don't quite feel it because it's pretty thick skin, right? Normally we are thin skin, right?
Stick my teeth in it.
It's thick in there. If this is like that, I will not feel it. So I think I'm a pretty thin skin person. So this temperature, you know, and the speed of sound, of course, changes with location. Okay, now, remember this is important. Try to convince yourself that you are waiting for UCS and go and try to lecture yourself on this. If you can lecture yourself, you will.
Hey, say hi to YouTube.
Oh, sí, eso.
Say hi to YouTube.
Yeah.
Say hi to YouTube.
Alright.
Hey, say hi to YouTube.
I think it is the quality. Yeah, eso es. This time got real. Es que la verdad no sé si. Real